Now our topic is electric power, and in this class we will be talking about one of the most important energy transfer process for human civilization actually, which is the process in which electrical energy is transferred into other forms of energy and electrical circuits. Well, in the use of electricity, there are two important energy transfer processes. The first one is the transfer or transformation of other forms of energy into electrical energy, which is the generation of electrical energy. And this is will be the process that we will discuss later when we come to Faraday's law. The second, which has to do with the utilization of this electrical energy, and this is the transform of electrical energy into other forms of energy like heat or kinetic energy or whatever. It is the processes, the transformation process that happens every day when you use electricity to run all the appliances or the devices that we are using in daily life. They might be bulbs, they might be electrical heater, air condition, electrical motor, your TV, everything. Okay, so it is this latter energy transformation process that we will be discussing today. Now, we start by considering a circuit, and a simple circuit, and we will demonstrate this for a very simple, the simplest of circuits, but the principle actually is the same when we have more complicated situations. So let's start by first trying to make sense of what the symbols in this circuit are, and what do we try to say when we draw such a circuit diagram. Now, we have circuit elements in circuits. These circuit elements are power supplies, for example. One of them is a circuit element like a battery, and usually we refer to it this way. We have a large line and a smaller line, okay? We put this minus, this is plus, to remind ourselves that this terminal is at higher potential with respect to this terminal, and therefore the electric field actually goes from up to down, okay? So it's in this direction. And so when you go from here to here, you are moving against the electric field. Also, you are moving in a potential rise, So as charge moves from here to here, it gains potential energy. So this is one circuit element. Another circuit element is the resistor, and usually we refer to it by this line, zigzag line, and this is the resistor. There is a switch. A switch is just, something that we need to close in order to open or close the circuit, and this is a switch. It has zero resistance. It's assumed that it has zero resistance. And then there is these connecting wires where we don't have circuit elements on them, between them. Okay? Now, it is important to understand and to note the following point. Whenever you have 2 points on a circuit with no circuit element between them, then these 2 points are taken to be at the same potential. So, for example, if you consider this line that connecting this point here and this point here, then B here and this terminal of the battery, they are at the same potential, and the same applies for each point on this line, including C. Okay, whenever I don't have a circuit element between 2 points, then these 2 points are taken to be at the same potential. This is the assumption we make when we draw these lines in circuit. So effectively, actually, point B and C are the same point. Now, if you do want to think of these as wires, B and C are connected by a wire, then the only way to have these at the same potential is to have this wire having zero resistance, because if they are the same potential, then delta V is zero, but delta V is I times R. And the only way to have this zero is to have, whenever you have an R, is to have an I flowing in the circuit, is to have R equal to 0. Of course, in real life, the connecting wires are not objects with zero resistance. But what happens is that usually their resistance is much smaller than the resistances involved in the other devices, like for example an iron or an electric heater or a light bulb and so on. Those elements have high resistances because they are the circuit elements where you want to utilize electrical energy and change it into thermal or light energies, and therefore through a resistance. So they have very high resistances. So we can ignore the resistance of these in comparison to this, and we can assume that they have zero resistance, and so the potential difference between them is almost is negligible, and so we can take them to be at the same potential. So the rule is, whenever you have 2 points on a circuit where there is no circuit element between them, the switch is not a circuit element, by the way, like a resistor, like a battery, a power supply, or like a capacitor, for example, or later an inductor. In this case, these 2 points are taken to be at the same potential. So this is something important. Now, when this switch is closed here in this circuit, a current flows in the circuit. Now, the current flows in the circuit. How do you find the direction of flow in the current? As I told you, in the battery here, the electric field goes from the upper on the positive terminal to the negative terminal. This is at higher potential, at lower potential. But if you look at this point, for example, point D and A are at the same potential as this negative terminal. And point C is the same potential as B, which is at the same potential as this. Therefore, in the resistor, this point C is at higher potential with respect to point D. So the current in the resistor will flow in this direction. Okay? So in the circuits, in the lines here, therefore, in the whole lines, the current will be flowing in this direction. But since the current flows continuously, then inside the battery, the current flows from the lower plate with lower potential to the plate with higher potential. Okay? And we will see what does this mean. Okay? And how is this possible? Because in this case, the current is flowing here against the electric field. So the electric field here is from upper to lower. The current is flowing against the electric field. Here, this is at higher potential than this, so the electric field is from here to here. So the charge, I'm talking about positive charge now because the current is the motion of positive charge, is flowing from here to here along the electric field line across a potential drop. So from this terminal to this terminal, from this point to this point. So the electric field is downwards and the current flows downwards. The positive charge flows downwards in this case. Okay? So this is what happens here. So here it will flow by itself because it's already at higher potential. It will move down to lower potential, and with the potential energy it has here changing into kinetic energy as it moves through the field. It's like when you drop a ball, a mass from your hand and release it. As it goes down a potential drop, it will lose potential energy, and this potential energy will transform into kinetic energy. So this is what's happening. Now, because I'm going to talk about energies, then I'm assume that the whole circuit is my system. That is the battery, the chemical energy that is included in the battery, and the resistor as a whole. This is my whole system. Of course, these wires also, as I mentioned, it's just they have no resistance. So, I mean, mainly this and this together are my system. So now, as the charge moves from A to B, it cannot move by itself because it will be moving against the electric field, because the electric field is going from the positive to the negative. It's from the higher potential to the lower potential. So the charge cannot go through a potential rise by itself, and external work must be done, and the transfer of potential energy should be carried out to the charge. So the potential energy of the whole system should increase when the charge is moved from here to here. Now, this increase in the potential energy of the charge, this additional potential energy of the charge, or the system actually, the charge, because the whole system is a single system, comes by at the expense of a decrease in the chemical energy of the battery. So the role of the battery in this case is to transfer, to do work on the charge that crosses it from the lower potential to higher potential, and this work will increase the potential energy of the system, and this increase in the potential energy will come at the expense of a drop in the chemical energy that is stored in the battery itself. So as the current flows through the battery, there is an increase in the potential energy of the system. On the other hand, as current flows through the resistance from this point to this point, okay, and charge flows from C to D, the charge is moving through a potential drop because this point is at higher potential like at this point. Therefore, there is a drop in the potential energy. Now, this drop in the potential energy, it's, as I mentioned, like dropping a mass from here to the ground, will mean that we will have generation of kinetic energy. But as the charges, as the there are collisions taking place between the charge carriers and the material of the resistance, this kinetic energy that is gained is immediately transferred into heat energy, which is internal energy of the resistance. So as the charge flows here, all the potential energy that it has lost as it moves in the field will transfer to kinetic and then immediately to heat energy or internal energy of the resistance. So what happens is that the potential energy loss here is transferred into heat energy. Note that in this point and this point are at the same potential, and this point and this point are at the same potential. Then as the current flows, the energy per unit time, potential energy per unit time that is lost here into or transferred here into heat energy is equal to the potential energy gain per unit time that happens here, because the charges are moving in both cases, the same charge per unit time, and the charges are moving through the same potential difference. Okay, so we have here a gain in potential given by when a charge Q passes, given by Q delta V, and we have a loss in potential energy, and we have a loss in potential energy here by the same amount when the charge moves from C to D. And this is loss in potential energy changes, doesn't go out of the system because this is part of the system now. It increases the internal energy of the resistor. Okay, so that's what I'm doing. It changes into heat. This potential energy changes into heat. Now, of course, as the resistor heats up, it will not keep this energy. It will heat the air about it, and it also emit energy in the form of thermal radiation. Okay, so now this energy is lost out of the system. So what's happening here? We have potential energy gain of the system, this potential, and we have a change of this potential energy into internal energy. But this internal energy is then transferred to the surrounding of the system, okay, which is air. And this is exactly what we want. We don't need the energy to be kept in the system. We want, for example, if this were a light bulb, we want this energy to be radiated as light so that we can utilize it, okay? And this is the process that is taking it. Now, as time passes, we will reach a point where the input energy of the battery is balanced by the output energy in the form of heat and radiation. And this is exactly what you want. So how much energy the battery is providing, potential energy is providing, is equal to how much energy is radiated by the resistor, and this is the energy that we utilize, the energy that we utilize in this case. Now, in general, of course, we can say that the rate at which the system's potential energy decreases here is equal to the rate at which the gain in the kinetic the gain in the internal resistance. Well, this is what we have just said. That is, as the charge moves across the resistor, it uses a du. It uses potential energy. There's a drop in potential energy, which is equal to the potential energy provided here. But this drop in potential energy changes into heat. Okay? So this is just a reiteration what I have said. Now let's quantify things. Now, the power, which is the energy per unit time, generated by the battery, the potential energy per unit time provided to the charge by the battery, is called the power. Okay? And this is at the same time equal to the energy per unit time delivered to the resistance, and in other words, it is equal to the energy changed into heat in the resistor. Now this power, which is equal to the rate of change of potential energy, is this. Q delta V is the charge that passes through the change in the potential energy when a charge Q passes through delta V. The rate at which this happens, because the potential difference across the battery is fixed, is just dQ by dt times delta V, and this is I delta V. So the meaning of this is that the battery provides potential energy to the system, increases the potential energy of the system. The system is the battery plus the circuit plus the resistor at a rate equal I delta V. So this is the amount of energy that is provided by the battery. And this is equal to the amount of energy that is changed per unit time, because it's power, amount of energy per unit time, that is changed into internal energy and then transferred out of the system. So for the resistor, this is also I delta V is the power delivered to the resistor. But if the resistor is ohmic, then I can write instead delta V I R, then you get I square R, or you can express it this way. So this is specific, this expression is specific for the power dissipated in a resistance, yani the power changed into internal energy, into heat in a resistor. But this expression is general. It applies to the battery, it applies to the resistors also. This applies to any circuit element, So because it is simply comes from here, which is very, very general. Okay? Whenever a charge moves between 2 points where there's a potential difference, then this is the change in the energy, and the rate of change of the energy is the power. So this expression is a very general expression, applies to any circuit element. When it comes to the resistor, this is specific to an ohmic resistor, which is the rate at which potential energy is delivered into other forms of energy. So this is basically the main or an outline of the major energy transfer process in the simplest of electric circuits, which is composed of a resistor and a battery. The system's energy is increased, electric potential is increased by the battery, and this potential energy is changed into internal energy by the resistor, and then eventually it's transferred out of the system. The rate at which this energy is delivered is equal to the rate energy is consumed. Okay, and this is conservation of energy. So this is the simplest process, and this is the most basic process. In more complicated circuits, the details are different, more complicated, but the principle is the same. There must be a source which raises the potential energy of the system, and there must be circuit elements which consume this, in other words, change this potential energy into other forms of energy. And the rate at which this is happening is equal to the rate at which the other is happening, so that conservation of energy is always observed. Of course, in SI system of units, I is measured in ampere, R in omega, and the potential difference in volts, and the power in this case will be measured as usual in watt. Now, keep in mind the following important point. In circuits, I said that when the charge moves from here to here, then the potential energy of this charge is changed by Q delta V, and then this amount of energy is the energy that is dissipated here. Don't understand that what happens is that a charge comes here, it moves across the battery, and then we have to wait until this charge reaches here, then dissipates the energy that it was given to it by the battery here, and so on. This is not what's happening. For the simple reason, because the charges, as we have seen before, in conductors are moving at drift velocities of 10 to minus 4 meters per second. But we know that when you close a switch, the lights come on almost instantaneously. Actually, what happens is that so it is not that the electrons that or the charge carriers that gain the potential energy there are those that we need to wait for them until they come here and dissipate that energy. No, this is not what's happening. What's happening is that once you close the switch, an electric field is generated in the whole circuit, and this generation of electric field happens almost instantaneously. It's at the speed of light, so it's almost instantaneous for practical purposes. And so the whole electrons and the whole conductors are put into motion at the same time. Okay, so this is what's happening. The current, therefore, is generated almost instantaneously all the way in the current through the circuit at the same time, and the current continues to flow. Current is not used up in the circuit. In other words, the electrons are not swallowed or go somewhere in the circuit. Okay, this is a misconception. What happens is that the electrons keep gaining energy by the electric field and losing that energy in circuit elements into heat and so on. Okay, so this is what's happening. It's not that the electrons are used up or the charge carriers are used up in the resistor and they are provided by the battery. So the battery is not a pump where it pumps electrons into or charge carriers into the circuit, and resistors or other circuits are not devices that swallow these electrons and that the battery provides. There is no such a thing. Okay, the electrons are already there and they remain all the time there. The issue is that the battery generates an electric field in the whole circuit, and the energy transfers that we have mentioned take place this way. And of course, this is just that trivial point. Now, we will talk about electric power transmission. That is how we transmit electric power from a place to place. And in particular, the issue that I want to address, or the question that I want to address, is when we transfer electric power from the places where they are generated, like electric power stations, for example, to other places. As each one of you know, we use high voltage lines. And you know this because it's very dangerous. You are always told that it's very dangerous to approach these because there are high electric field and there are high voltages. Okay, and so we will answer the question why, when we transfer power over large distances this way, we are using high voltage. Actually, to put it right, we are using very high voltages and small currents. Okay, why is this so? No, we'll answer this question because it has to do with what we have just learned about power dissipation and resistances. So now we know that the power dissipated in resistance equal I square R. Now when you want to design a transmission line, there is a limit for how low you can make the resistance. Because what was the resistance? You remember, it was for a conductor. It was rho, resistivity, multiplied by A divided by L. Now L you cannot control because you want to transfer power from somewhere to somewhere else. Okay, so L you cannot control, so you cannot make it shorter. Okay, you cannot build a power station next to each facility that's going to use electric power. So L you cannot control in most cases. Now A, which is the cross section of the wire, there is a limit for that because you know it's costly and also you have to carry them through you know, towers and so on, so it becomes very heavy and so on. So it's practical. For practical reasons, there is a limit on the resistance. So there is a limit of what we can do for the resistance. So to make the power lost, this is what? This is the power lost into heat. Okay, the rate at which electrical potential energy is changing into heat energy. And you have to reduce the I. Now, at the same time, the power is given by I delta V. That is the power delivered by any power station. You know, there is an output for the power station that you are want to transfer power from it. I mean, it's just, you know, they are rated at megawatt, gigawatt, for example. Okay, so they generate power as much as you need, and so this is usually high power. Now, this high power is delivered by that can be is expressed as the current through the wires when you transfer it through the wires, multiplied by the potential difference. Now, you can keep P, this power. You can have this power transmitted because it's fixed. It's the output that comes from the power station. You want to transmit it. So you can transmit it by making delta V high and I low, or making I high and delta V low. It's up to you how you design it. Now, taking this into consideration, it's advantageous for us to keep I small and delta V high. This is why we usually, when we transmit power over lines, we keep delta V high, thousands of volts actually, to keep I small, because that power you want to transmit it, that energy per unit time, you want to transmit it, but you want to make sure that this is small, this loss is small, because you don't want it to be lost, not now at least, in heating the atmosphere, okay? You want it to go without minimum loss to wherever you want it to go, and so you minimize I, so you increase delta V. This is why we have high voltage transmission lines. Let's consider an example, a simple example, just which applies the ideas that we have talked about power and other things. So we have electrical heater, and this is constructed by applying a potential difference of 120 volts. So and there is a wire, and this wire has a resistance of 8 ohms. Okay, so what is the current carried by this wire, and what is the power rating of the heater? Well, the first part is very easy to find. The power is just, the current is just delta V by R. So this current, this wire will have 15 amperes of current flowing through it, and this will generate for us an electric heat at a rate of I square R, which is 1.8 times 10 to the power joules per second, or 1.8 times 10 to the power 3 watt, yeah, 1.8 kilowatt. So this heater will be rated at 1.8 kilowatt. Okay, so this is the power lost, and so per second you will be given 1.8 kilojoules of electrical energy, electrical potential energy, and this 1.8 kilojoules of electrical energy will be lost in the resistor. So, and then transferred eventually into the water, and this is why you heat the water. So this is what's going on here. Now, this is an alternation of this problem that you will try to do yourself. So if we increase the potential to 240 volts rather than 120, what will happen in this case? Try to think it. Okay.